Hey guys, this is Saptarshi here and welcome to our YouTube channel. So last class we have revised the concept of gradient descent, stochastic gradient descent and mini batch gradient descent. And we have looked at a particular type of optimizers called as momentum based optimizers. So if you want to take a quick look, I suggest you look at our previous video. Today we are going to look at another optimizer called as AdaGrad. Okay, and there is one slight variation of AdaGrad which is called as AdaDelta. So we'll briefly describe that as well. Okay, so let's go back to our central equation of gradient descent. Okay, so gradient descent is an approximate algorithm which tries to find the parameters of the model such that those parameters minimize the loss function. Okay, so if and this learns the parameter iteration from iteration, epoch from epoch, right? So the current iteration parameter value or weight value. So we are sticking to weight because we are talking about neural networks. But this discussion can be generalized to any machine learning model with the use of theta. So here what we are doing is we are updating the parameter value, the weight value, based on the previous iterations parameter value or weight value, learning rate, and the derivative with respect to the weight. So this is actually a shortened expression. Let's expand it. So generally we represent the cost function by z. So it is del of z, del w, where we are talking about del w old, right? So this is the central equation, and what we saw in momentum based methods is we actually played around this del w, right? So if we want this weight to change in a certain manner than the normal manner, one of the things that I can control is this del w. So what we saw is that in our vanilla gradient descent, we are concerned about the current gradient only. Okay. However, in case of momentum, we were keeping kind of a history, right? And we are using different weights. Okay. The current gradient was getting the maximum weight, and slowly the weight was getting decayed. So basically it uses a parameter beta which does this, and momentum brings an effect of exponential moving average. Okay, so another parameter that you can evidently understand we can play around is this learning rate. Okay, so that is the motivation of our AdaGrad optimizer. Okay, now you might question that why do we really need to change the learning rate? Okay, so the idea is like this, that if you start with a regular or normal learning rate, okay, and you will converge slowly. So if this is your starting point, follow the blue line, all right. So you will converge here gradually, right? And you might not be happy. You might think that this is quite slow. Okay, so what you want now is, what you can do is you can increase the learning rate, and as a result you can jump. So if your starting point is here, you can jump from here to here. Okay, and then from 2 to maybe 3, 3 to again 4, 4 to again 5. So now the steps are high, but convergence is still not happening, right? So rather than that, what you want is you want to change the learning rate. Okay, you want to change the learning rate from one step to another. Okay, so this is one thing which is dramatic. Earlier, when the training was happening, the learning rate was same for the entire training. Now you are going to change the learning rate gradually. All right, and this is not a new concept. Okay, so there was already a concept called as annealing. Okay, which is in the simulated annealing. So basically there are two type of algorithms. One is called as hill climbing, which is a very greedy algorithm. Okay, which can get stuck at the local minima very easily. And another set of algorithm which is called as random walk, which is completely stochastic in nature. Okay, so what annealing suggests is that you start your solution space by random walk. Okay, because then there is less chance that you will get stuck in a local minima. And when you are moving towards the optima, you gradually move from random walk to hill climbing, right? So that you don't actually get stuck or get deviated from the optimal point. Okay, so that is one of the motivations of this AdaGrad algorithm. Okay, So here is a graphical representation, a graphical comparison between gradient descent, stochastic gradient descent, and AdaGrad from one of the papers on their problem. And if you see that, you know, compared to gradient descent, stochastic gradient descent actually converges faster, okay, and actually gets a lower loss value. So this is the loss value that you are minimizing, all right. However, you see AdaGrad actually have done better than both of them. Okay, so this is one of the problems, not all the problems. Now, the question that comes to all of our mind is that how do I change the learning rate now? Okay, so let's look at that. Okay, so this was our original equation. This is our learning rate. So what we do now is, instead of writing in this manner, we write it in a more generalized manner. Okay, so the new is replaced by t and old is replaced by t minus 1, and this learning rate we are calling as neta t over here. We could have as well called as, you know, neta t minus 1. It depends on the convention, but it essentially tries to tell you that in each step your learning rate is different. Okay, now how this is different? So neta t is actually a ratio of the original learning rate and square root of alpha t plus epsilon. Okay, so epsilon is a small value. Why we use it? Because if anytime this alpha t is 0, you know, we don't want to get a divide by 0, and we don't want our algorithm to abnormally terminate it. Okay, so what is alpha t? Alpha t is actually nothing but, you know, summation of the square of the derivatives. Okay, up to that point, you see. Okay, so let's when we look at an example, it will be more clear. So let's look at an example. Let's say we started with a you know, del w square as 2.25, okay, and alpha t is 2.25, right? So, you know, this is the only thing that we have added over here. And let's say learning rate was 0.04 and epsilon had a value of 0.01. So uh, as a result of this decay, in the next step, our learning rate changed to 0.18. Let's say in the next step, the derivative is 1.5. So alpha t is no longer 2.25. It is 2.25 plus 1.5 because it is maintaining the history, right? So it is 3.75. On the same learning rate, the same epsilon, your learning rate now comes down to 0.01. Okay, and you know, next step maybe it is 0.9. So your alpha t is again 0.9 plus 3.75, which is 4.65. Neta and epsilon doesn't change. When you divide this, you get 0.008. So that's how in AdaGrad your learning rate goes down gradually. All right, okay. Now the one important thing to understand is, so AdaGrad, it not only changes the learning rate from one iteration to another iteration, actually it has another advantage. The advantage is that all the neurons now has a capability to learn at a different rate. Okay, so this is something also very important. Okay, so let's say, you know, you have some features with very high variance. Okay, so we took the previous example that we discussed where you see the learning rate has changed like this. All right, whereas, you know, if your feature has a low variance, okay, so then of course your derivatives will also be smaller, right? Because the change with respect to error, because there is very less deviation in the input feature, as a result the derivative is also not changing much, right? So in that case, when we do the calculation, you see, you know, it is coming down at a much lesser rate, right? Because if I decay when there is less variation and I decay the learning rate very fast, then what will happen is, for those features the weights will not be learned properly. Okay, so this is also one of the important advantages of AdaGrad. So AdaGrad doesn't only change the learning rate from one iteration to another iteration, but actually different neurons can learn at a different rate. Okay, so these are two fundamental, you know, striking points of AdaGrad. All right, so one of the issue with AdaGrad is the learning rate may be very close to 0. Okay, So you can understand, right? So when you are, it is decaying, and so at one point of time, the learning rate can be very, very less. Okay, so this may not be a very desirable characteristic. So what was suggested was that instead of using all the square derivative, we can use a window size. Okay, so let's again understand this with a data example. Okay, so here what we are saying is that we will only consider the past two derivatives, not more than that. So a window size of 2. So we started with 2.25, so alpha t was 2.25, no issues. Then 1.5, so it got added. However, when we are moving here, if we have used AdaGrad, our value would have been, alpha t value would have been 4.65. But in case of our AdaDelta, where window size is fixed, we are only going to look at past two values. So this value will be 2.4. So if you compare, AdaGrad and AdaDelta starts similarly. Second step is also similar, but in the next step, if you see, learning rate has actually increased a little bit, right? So it is not going down like it will happen in AdaGrad. Okay, so this is one of the advantages of AdaDelta. So this was a paper from 2012 by Jailer from Google. Okay, and I just want to look, I want to take you through the abstract. So it wasn't a novel pre-dimension learning rate method, part dimension learning rate method. So I was focusing on the, per neuron kind of a learning rate, right? Which is AdaDelta. This method dynamically adapts over time using only first order information. First order information because the derivatives that I'm dealing with are first order, and has minimal concept computational overhead beyond vanilla stochastic gradient descent, right? So this method requires no manual tuning of a learning rate and appears robust to noisy gradient information, different model architecture choices, various data modalities, and selection of hyperparameters. Okay, so they tried this on MNIST and another data set, large scale voice data set. So I will show you the result they got from MNIST. Okay, so they have compared SGD, momentum, AdaGrad, and AdaDelta, right? And if you see here, SGD gets a quite a less loss rate, all right? And if you look at momentum is sketchy but achieves probably the best loss rate, okay? And the green one is your AdaGrad, and compared to AdaGrad, if you look at the blue one, though it is a little sketchy, the loss value that it has achieved is better. Not only that, though, momentum has outperformed when you are at 50 epoch, but this gives a very good early convergence sign. Okay, so that brings us to the closer of discussion of AdaGrad and AdaDelta. So these are also two optimizers which are quite popular and needs discussion. Okay, so just to summarize, actually AdaGrad plays with the learning rate. Okay, but using the AdaGrad you can reach a learning rate which is very close to 0. That's why you sum up the square of the derivatives only up to a particular history, and you call such a method as AdaDelta. Okay, thanks so much guys for watching this video, and if you have liked it, found it helpful, please give your endorsement by liking, commenting, and subscribing. Thank you so much guys. We would love to see you again.